Hello everyone, my name is Mahad Ali Khan and today we are going to study the chapter 0 of microcontroller and embedded system. This book is basically as a reference to the second edition of the Muhammad Ali Mazadi, Stephen Naimi and Sarmad Naimi. Stephen Naimi, and this topic basically discuss the internal organization of computer, the different parts of a computer, input output memory and CPU central processing unit. It discusses the connectivity of different parts of the connecting memory of central processing unit, connecting input output of central processing unit, and how the computer basically works. The internal organization of computers basically includes central processing unit, memory and input output devices. Input for example keyboard, mouse and sensor. Output basically example of output are basically LCD, printer and hands of a robot. Then we have the memory, everything that can store, retain and recall information is known as memory, which includes hard disk, piece of paper on which we write contains some memory for etc. And then we have memory characteristics. Memory characteristics basically includes the capacity, the number of bits that a memory can store, for example 128 kilobytes and 256 megabytes. Its organization basically includes how the locations are organized on a register, and for example 4 gig memory, 4K memory, 128 and one it has 128 location. 128 basically refers to 128 location, which basically in this we can say it has 0 to 127 memory locations in which different types of data can be stored. Its access time, how long it takes to get different data from memory. There are two types of memory: semiconductor and non-semiconductor. Semiconductor memory basically includes RAM-ROM. RAM includes mass-ROM, PROM, programmable ROM, erasable PROM, and electronic erasable ROM. Flash ROM. RAM basically include SRAM, static RAM, DRAM, dynamic RAM, NVRAM, non-volatile RAM. Then we have the mass ROM programmed by the IC manufacturer. And then we have the programmable ROM. It includes one-time programmable. It is one-time programmable. You can basically program it only once. Then we have the erasable programmable ROM, which we can erase the data. You can shine ultraviolet radiation to erase a program. Erasing basically takes 20 minutes. The entire content of ROM are erased in this. Here we have an example of simple erasable ROM which contains 24 pins and access at a voltage of 25 volt. Its access time is 450 ns. Its organization includes basically two ROMs of 8 bytes, 2K memory stored each. Its capacity is 16K and the parts its code is 2716. Then we have the electrical erasable programmable ROM, which is erased electrically, erased instantly. Each byte can be erased separately. Uh, in this we can see that there is a ROM of 8K 8K 8 8K 8-bit each. Each byte can be erased separately. Part number 2816825. Its capacity is 16K. Its organization is 2K. 8 its speed is basically greater than the speed of the erasable programmable ROM. It has similar 24 pins, and but it operates at the voltage of 5 volts. Then we have the flash memory. Flash memory basically includes erased it's erased in a flash, the entire device is erased at once. Then we have its table, the part number. For example, we can say that it is 228F25620. Its capacity is 250K and its organization includes 32K of 8 bit each. 8 bit each. Its speed is 200 NF and its plans of its pins of 32 pins. It operates at a voltage of 12 volt. Then we have the semiconductor memory. Then we have a semiconductor memory. Semiconductor memory includes basically RAM-ROM, in which we have discussed earlier. Then we have the spam static RAM, and now we have RAMs. Static RAMs made up of flip-flop transistors, and its advantages is it is faster, no speed for refreshing. Its disadvantage is high power consumption, and it's very expensive. Then we have the dynamic RAM. It's made up of capacitors. Its advantage is less power consumption. It's cheaper in price and it has a high capacity. Then its disadvantage is it is slower in speed and its refresh. It needs refresh every time. Then we have non-volatile RAM. It's made up of SRAM battery control circuits. Its basic advantages is it is very fast, it's infinite program erasable cycle, and non-volatile. Its disadvantages is it's very expensive. Internal parts of computer CPU tasks it should execute instructions. It should recall the instructions one after another and execute them. Then we have the connecting memory of CPU. This is a memory pinouts of a CPU in which we have the ground, the VCC, the numbers to 0 to 7, which basically includes 8 number pins, and A0 to A infinity numbers of data address lines. Here we have a graph reading from the memory, and there is and the connectivity of CPU through its pinouts. Achha. Now we have the connectivity of input output of to CPUs. To CPUs there is a network that is connected. The graphic card, a sound card, a keyboard, and the mouse is also connected to the pinouts of a central processing unit. Here we see that there is a address bus, data bus, and control bus. Read write operation. It basically reads and writes the memory. It basically reads and writes the memory of each bits coming from the input output operation of the infinite numbers of operations. And then we have the connectivity input output and memory or to central processing unit. How it basically refers to how the memory of input output can be transferred from the input output to memory locations to read write and address bars to the output pins of the CPU. Now in this we can see that there is a register of bits of infinite numbers, and we say that how could we make the logic circuit. We see that if the topmost address form is 0, then the fifth and the to address from address form is 0 and to address form is 15, then we can say that then the 1111 bit is refers to the F numbers. Now we have the decimal to binary conversion. Decimal to binary conversion, we say that we have to convert decimal number 25 to a binary number. We divide each number of the decimal by 2 to convert into a binary, and the most significant bit which will be the last bit, we will count from the most significant towards the least significant bit, so it will become 1100 when we go from bottom to top. Then we have the binary to decimal conversion. We have to convert the binary number to decimal number, we have this, and we will multiply each number by and it will generate a carry, and if it generates a carry we will add this term, and we will add this term and we will combine this to see the total number of decimal occur. So if we multiply the 2 raised to the power of 0 to 1, it will generate a carry of 1. We will add it and so on. It will become 225 to the binary to the number of binary to the decimal 10. Similar as in example 3, we will now discuss this, and example 4 we will see that we have to replace into a binary number into hexadecimal. We will make pairs of 4 each, and from the first, from the middle, and from the last we will make 4 pairs of each 4 number of bits from each binary number. Then we will see that 1001 refers to 9 in the number system, and 1111 refers to F, and 0101 refers to F in the binary number system table. So it will become 9F5 in hexadecimal number. Similar in example number 6 and example number 7. Now we have to do addition of binary numbers. For doing addition of binary number, we have given decimal number 13 and 9. We have to add both numbers. We know that the 13 in binary is 1101 and 9 is 1001. When we have to add it, both the binary number, we will add 1 plus 1 into 0, and it will generate a carry of 1. Then 0 plus 0, it will generate a carry. Then the 1 which was generated in addition of 1 plus 1 will be add to the total amount. Then 1 plus 0 is 1, and 1 plus 1 is again 1 0. So through this we will do addition of binary numbers. Now in example 9 we have to take 2's complement of 100111101. First we have to take this binary number and shift these numbers, as 1 is becomes 0 and 0 becomes 1. Then we will add the 1 to make it a 2's complement. Then we will add 1 to the 1's complement and write the final answer of 2 complement. Then we have the ASCII number. We have to remember these memory numbers. Then we have these control characters. These are the full form of these. Then we have another example for address decoder. We have to design an address decoder for address 300H to 300FFH. From address 300H it is 0011, and so on the bits are 0. To address 3FFH we see that the 0011 and the 0 bits from the 300 will be shifted towards the 1 bit number. An easy way of designing is mentioned in the picture. Now we'll discuss what's inside the CPU. A CPU, inside a CPU there is a processing counter, there is a instruction decoder, there is a arithmetic logical unit, and there are registers. Register value depending upon its value given. So we have given the condition and one, and the program counter starts. There is the instruction given to us will calculate the values, and databus will manage these values. Then the databus will transfer it to the read drive, transfer it to the register value A. When a new value will be generated, the new value will will go from the input output data buses towards the memory location of part A, and so on and so on. There will be, when the new value comes, the old value will change its value from the topmost to the towards the bottommost. Here we can see the value 9 is shifted towards the register B, and the new value coming will sit on the top of the value. Then we see how instruction decoder works. There are two types of code and operands. Now we see that non-Neumann and versus Harvard architecture. In CPU, the data buses in CPU, the code memory he transfers the irreversible data buses, and data memory transfers the reversible data buses. The data buses from the CPU is transferred towards the code memory in irreversible direction, and also then data memory in its irreversible direction. Similarly, control buses. Now there is general purpose microprocessor and microcontroller. Microprocessor and no RAM ROM input output ports or chips itself. Microcontroller, microprocessor, RAM, ROM, timer, input output ports on a single chips. And 1809 Intel is an example of this. Its application basically include TV, remote control, video games, robots. Its general purpose microprocessor versus microcontroller, data buses, address buses, and control buses. General purpose microprocessor includes RAM, ROM, serial A, time, R, and input output. Now we will discuss the embedded system. An embedded system is controlled by its own internal microprocessor or microcontrollers as opposed to an external controller. A PC is connected to various embedded products such as keyboards, printer, modern disk controller, sound card, CD-ROM, driver, mouse, etc., and so on. The embedded products basically includes computing, cars, communication, and cards. Embedded products are consumer current connectivity. Choosing a microcontroller basically refers to the speed, packaging, and power consumption, the amount of RAM ROM on chips, the number of timers and output pins on chips, cost per unit, availability of compiler, simulator, debugger, availability of chip in market. It depends on these values. The AVR microcontroller family, the basic architecture of AVR was designed by two students of Norwegian Institute of Technologies NTH FL Elif Egil Bogen and Vegard Wolen, and then was bought and developed by Atmel in 1996. The AVR stands for Advanced Virtual RISC or FL and Vegard RISC or FL and Vegard RISC. The AVR is a 8-bit RISC single chip microcontroller with Harvard architecture. RISC and CICS stands for Complex Instruction Set Computer. A large number of instructions, typically from 100 to 250 instructions. Some instructions that perform specialized tasks and are used infrequently. A large variety of addresses modes, typically from 5 to 20 different modes. Variable length instruction format. RISC stands for Reduced Instruction Set Computer. It's relatively few instructions, relatively few addresses module. It fixes the length easily decoded instruction format. Then there is Harvard and von Neumann architecture, von Neumann Princeton architecture.